All right. So again, today we're not going to do lab just because I haven't quite got it figured out. But I figure we'll make use of the time and at least we'll probably won't go the full. No, I know we won't go the full 3 hours, but we'll do a bit here so that we can kind of keep moving along. And before we get into new stuff, I did want to ask if people have any questions about the homework and see how things are going. And I see that Chase says that he'd like to look at number 106. Is that chapter 9? I just want to confirm. Yep, okay. So let's look at number 106 in chapter 9. So I'm going to pull up the book and we'll go ahead and look at that. I'll share my screen so that we can all see it. All right, so y'all can see my screen now and I've got volume 1 pulled up. So let's run down here to chapter 9. Oops. I'm going too fast for it. Chapter 3. Six. Oh, I'm getting close. All right, so here we are. We're in chapter 9. All right. So 109 says, where is the center of mass of a semicircular wire of radius r that is centered on the origin, begins and ends on the x-axis, and lies in the xy plane?
You said 106, not 109.
Oh, thank you. Okay. So I was all excited. 109 is actually very similar to the example we did before. So let's look at 106. Thank you for that, by the way, Rob. So two identical billiard balls collide. The first one is initially traveling with this velocity, and the second one with different velocity. Suppose they collide when the center of ball 1 is at the origin, and the center of ball 2 is at the point 2r, 0, where r is the radius of the balls. All right. So this one is basically going to be a conservation of momentum kind of question, right? We don't know what kind of collisions we have, so we can't assume that the kinetic energies are the same, but we do know that the conservation of momentum has to occur, right? So we want to figure out the final velocity of each of the balls. So I'm going to really quickly here switch us back to the whiteboard, and we'll see if we can kind of work this guy out. So we'll stop sharing. All right, so I'm going to go to the whiteboard here, and I'll just rewrite this review stuff in a second. So let me just do this again. All right, so we've got a couple of different velocities. First of all, the ball's locations. We've got the one of them centered at the origin. So there's ball number 1. And then ball number 2 is going to be centered over at 2r, 0, which means it's over here. We're going to assume, oh, sorry about that, guys. All right, so we're going to assume, not assume, we're told that they have the same radius. So these are the two centers of mass. All right, and then we also have velocities, right? So the first one, the one that was centered at the origin, it says it has a velocity of 2.2 comma, minus 0.4. So I'm going to write them in that component form here. So 2.2 minus 0.4. All right, so that's V1, so that's this guy. And then V2, it was moving at minus 1.4, 2.4. All right, now the other thing that we don't have are the masses. But if you go back and you look at that question, it does say that they are two identical billiard balls. So we're going to go with that they have the same mass. And let's just call it M. Okay, so we've got mass M. So for any one of these, we want to do sort of the before collision and after collision calculations, because then we can set those two equal to each other because we know we've got conservation. Oh, and I just noticed this is starting to look like a face. I know it looks like other things too, but we're not going to go there because we're on record. All right, so in terms of the velocity before and after. Okay, so let's look at before, and we're going to have two momentums. So we're going to have P1, that's the momentum of the first guy, and that's going to be mv1. And the second one, we'll call it P2, that's going to be mv2, so they're still the same. So in terms of total, we want to combine these. And so we're going to get mass times the sum of the vectors. So we can just add these up component by component, and we're going to get mass times 0.8, comma 2. All right, so before we go any further, we good with that? Quick thumbs up or a thumbs down?
Thumbs up.
Is that 0.8, comma 2, is that like the resultant of the velocities, or what is it?
They're the
Correct.
X and Y's.
Those are
Okay.
the X and Y components of these two vectors. So
Okay, I see.
we do add them together, right? We're going to take P1 plus P2, and since they've got the same mass, I can factor it out. So I just need to
I
add their two
understand.
velocities. And since they're in vector form, right, in the component form, I'm just going to add components. So 2.2 plus minus 1.4, that's our 0.8. And then minus 0.4 plus 2.4 is our 2.
Okay.
Okay? All right, so that's our momentum before. So now let's go to the after. Now, after, we don't know anything about the velocities. In fact, that's what we're trying to find. If you go back and it says, look at the question, and it says, what is the final velocity of each ball? So I don't know what those are. So what I'm going to call them is maybe this. So the first one, P1, again, it's going to have its mass, but it's going to be times some velocity. I don't know what it is, but I'm going to call it Vx1. And how about Vy1? So it's going to be the X component of velocity and the Y component of velocity. And the sub 1 is just telling me that's for the first one. So I'll do the same thing for the second. So we're going to get P2 is equal to M times Vx2, comma Vy2. Again, add them together. And what I'm going to get for a total of P1 plus P2, we're going to get our mass times, well, it's Vx1 plus Vx2. I'm going to add those component. And then similarly, I'm going to add Y components. So I'm going to get Vy1 plus Vy2. So a bunch of unknowns. I have no idea what those are, but I do know that however these things get added together have to be the same as what I had before the collision. All right, so far so good? We still thumbs up?
Same.
All right, getting some thumbs up. Good, 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 good.
You do
All right,
that.
well, we know that this has to be conserved. So we know that these two have to be equal to each other. The mass doesn't matter. I can completely eliminate the mass. It's not going to do anything. That's why they didn't even give it to us. By them telling us that they are the same, that they're identical balls, we know that we don't have to worry about that. So let's look and see what this now tells us. We've got the 0.8, that's going to have to equal the Vx1 plus Vx2. So the sum of those two x components still has to equal 0.8. The y components also are going to have to equal 2. So I'm going to write this up here just to start keeping track of we're creating a system of equations, basically. We've got Vx1 plus Vx2 equals 0.8. We also have Vy1 plus Vy2 is equal to 2. All right. So do we have enough to solve this now?
I don't think so.
No, why not?
There's just multiple like unknowns.
Yeah, if you look at this, we have 4 unknowns. The 2 x components and the 2 y components, right? So there's 1, 2, 3, 4 unknowns. Unfortunately, we only have 2 equations. So somehow we have to get 2 more equations. We need to know something about them and see if we can do something with that. All right, so what do you guys think? What can we do here? Thoughts, ideas?
We have the original equations for each momentum of each ball. And since they're the same, sort of, maybe we could add those as well to this system.
Okay, so in terms of adding the original 2 momentums, that's what this is right here. This one down there was found by adding the 2 momentums. So we actually already did that, Bradley. Other thoughts? Is there anything we missed in the wording?
I don't think so. I'm rereading it right now, though.
Okay, I'll pull mine back up. It says, 2 identical billiard balls collide. Okay, so the identical we used, that's the same masses. The first one is initially traveling at 2.2 meters per second in the I direction and negative 0.4 meters per second in the J. And the second one is moving at negative 1.4 meters per second in the I and plus 2.4 in the J. So suppose they collide when the center of ball 1 is at the origin and the center of ball 2 is at the point 2r0, where r is the radius of the balls. What is the final velocity of each ball? All right, well, we took care of the velocities. We definitely have those, right? And we've got it drawn so that the centers are at the respective places. But the one thing we really haven't used, and Victor kind of just said here, you know, he put direction with the question mark. We haven't used the fact that they're at exactly these points. So maybe we think about direction. Maybe we think about these momentum vectors in terms of direction and all that. What do you think? Will that help us a bit?
I think so.
So let's try doing a little bit of geometry. So I'm gonna keep all this up here because I think this is important information. The calculation stuff I'm gonna eliminate. But I'm gonna try to draw the pictures a little bit well, as close to accurate as possible. So the first ball was at this point when the collision happened. The center mass was right here, and we had a vector that was 2.2 comma minus 0.4. So I'll even try to do this little trick where I have the same lengths on my axes. Okay, so this guy is going at 2.2, so right 2.2 and down 0.4. Looks something like that. So that's our velocity vector as we come in. All right, so then the other one has a velocity vector of minus 1.4 comma 2.4. So it's going to be centered out at 2r. Now I don't know what that is. I don't know exactly where 2r is, but I do know what that vector is going to look like. If I'll just start it from the origin. I'm going to go back. Sorry about that, guy. I'm going to go, sorry, right. No, wrong one. Minus 1.4. So I'm going to go minus 1.4 up 2.4. So that's what the other one looks like. So this is V1 and V2. So if we multiply by the mass, so we get our momentum, all that's going to do is stretch these things, and it's going to stretch them by the same factor. So I'm not going to bother with it. I'm just going to assume mass 1. Okay, so the mass is just 1. If it's not a kilogram, it's 1 mass of the balls, all right, whatever that happens to be. Okay, so those are the two momentums, and of course, if I add them together, I could geometrically add those things together, and I'm going to get the resulting vector, which is still this 0.82. It's going to be the resulting vector that looks something like that. All right, well, we still haven't taken R into account. So, any great ideas? Give me 1 second here, guys. My phone is buzzing off the hook, which is making it fall over, and I know you guys can hear it, so I'm gonna let's fix that real quick. Okay, so what are we gonna do?
Draw a triangle, perhaps, with one of them. Assume the
So when you say
hypotenuse
draw the
is the
triangle,
radius.
you mean get the components?
Wait,
Like-
are we trying to get a new vector when we have two vectors?
So what do you mean by a
A
new
resultant
vector?
vector, isn't that cross multiplying? Or X? You cross them.
Okay, so if we cross them, that will give us something that's going to be in the z direction. But is that going to give us anything momentum?
No.
Because we never had a cross
No,
product
it
in
doesn't.
momentum.
No.
And the vector that we obtain from these two is actually found by adding them.
Yeah.
So like this vector right here, that 0.8 comma 2, that is what the total momentum is going to be also after the collision. Okay, well, what about this? What if it was an elastic collision? What if it was completely elastic? Would we be good?
Yes.
Get a yes with a question mark on it.
Let me look real quick.
Well, what does elastic tell you?
No
No
loss.
energy is lost.
Okay, so that tells you there's no loss in energy So we could take our conservation of energy, take your 1/2 mv squared, and you could set those equal to each other, and that would now give us another relationship between their velocities. And that would give us 2 more equations. So that would definitely work in terms of getting us a system that's big enough. But is this elastic?
I think it's safe to assume so.
So you want to assume so just to make the math easier?
Well, no, it's because they didn't specify whether or not there was friction. They also, yeah, I'm going to assume so.
What do the rest of you guys think?
I think, yeah, I think so, because yeah, they never really specified. So
They also didn't specify whether or not the thing we were using to hit the balls had a velocity as well, or momentum for that matter.
Well, in terms of whatever started the process of these balls, that's kind of irrelevant, because it's at this moment, what are their velocities, what's going on. Well, let's try this. Let's actually see if it were elastic. Let's see what that would give us. So we're going to go with, let's try it. Let's assume that it's an elastic collision. So now our kinetic energies have to be equal. So if we think about our kinetic energies, 1/2 mv squared, but this is the magnitude of the velocity vector. So if we go with the before, we're going to have a kinetic energy 1 is going to be 1/2 the mass of the object, which we assumed are just the same. But then in terms of its magnitude, this is going to be the square root of 2.2 squared plus negative 0.4 squared. So I'm using the components from the first vector to get its actual speed, because that's what the speed is. So we're going to have 1/2 mv squared. So notice, because I'm not going to do this for the next one, I'm not going to write the square root and then the square, because they cancel each other out. But that's for the kinetic energy of ball 1. For ball 2, it's going to be similar, except it's going to be minus 1.4 squared plus 2.4 squared. Again, it's the square root being squared. So this will get me some energies. In terms of the after is going to look similar, except this is going to put back in those Vx1 and Vx2s. So we're going to get kinetic energy 1, 1/2 the mass, times Vx1 squared plus Vy1 squared. Same deal. We're going to take the square root and then square it, but we're taking the components. And then for kinetic energy 2, same story, except put subscripts of 2. So Vx2 squared plus Vy1 squared.
It's the same thing.
Vy2, sorry. So we add those together. That's going to equal this. The 1/2 m's are going to go away. But this is going to get us another equation in terms of Vx, in terms of all these guys. But here's the deal. This is only going to give us one more equation. So even if we assume that it's elastic, it's actually not enough. We still don't have enough information to know what's actually going on. So this is when we do a collective crap. Well, I don't want to give it away yet. I want you to keep working on this and thinking about it. But it definitely has to do with the positioning of the balls. So the fact that they're at 0, 0 and the other one's at 2R, 0 is going to come into play. But I want you to think about it a bit. See if you can figure out a way to rectify this. All right. So I know you're going to hate this when we do homework problems, is there are going to be plenty of times when I don't just tell you the answer, because I want you to experience trying to figure it out. All right. So that's one of these, but at least this is the start, right? You want to start by looking at the individual momentums, add them up, make sure that it's conserved. In terms of, is the energy conserved? You may not want to assume that just yet. All right, because yeah, you may not want to assume that just yet. I haven't done this problem, so I don't know for sure. But usually you don't want to assume a collision is elastic. You only want to do that if you're told that it's elastic, because again, out in the real world, elastic don't really happen. If you're playing pool and you've got billiard balls that are hitting each other, it's not an elastic collision. So that's not a good assumption to make. Anyway, I'm going to ask if we're good with this, and I know the answer is probably no, we're not good with this. But hopefully at least you feel a little bit better about how we need to start going about this. But I want you to think about it a bit more and see see if you can figure out how we use the locations of the center of mass to help us out. Okay. All right. Other homework questions? Other things we want to look at? All right. Well, hearing no anything, I'm going to assume that we're in general feeling okay with the homework. But yeah, 106 is a tricky one. So keep thinking about it, and we'll probably, not probably, I'm sure we'll talk about it again on Monday. All right. Well, let me just review a little bit about what we talked about last time. And we're going to keep going down this path. So we started talking about rotation, and I threw all kinds of things at you that you've probably not seen before. So we've got angular velocities and angular accelerations, and now there's tangential accelerations and radial accelerations and all that. So let me just kind of bring this back to the forefront of our mind before we move on to how we use those things and what we do with them. So I'm going to go back to the So let me just write some things up just to kind of refresh your memory. So some things that we talked about last time. We had arc length. And arc length, we use the letter S. And it literally is what it sounds like. It is the length of an arc of a circle as we go through a certain path. Okay, so that was S. All right, then we had omega. And omega, this was angular velocity. So it's the same idea as linear velocity, but instead of a distance per time, it's an angle per time. We also had angular acceleration. We use alpha for that. So angular acceleration, this is the change in angular velocity. And so angular acceleration is really a changing of the rotation. Are we speeding up the rotation, slowing down the rotation? Are we changing the direction of the rotation from clockwise to counterclockwise or vice versa? That's what alpha is going to calculate. In terms of some other linear quantities that we talked about in here, I want to bring back. We had v sub t. This is our tangential velocity. And so that's the velocity that's tangent to the path. So if we're going around in a circle, it's always going to be perpendicular to a radius. So we also had tangential acceleration. So the same idea. And then we had A sub c, which was centripetal, sometimes called radial acceleration. And so that's the acceleration that points towards the center of the circle. So let me just draw here. Let's say we've got a circular path. Not much of a circle. It'll do. So we've got a particle here that's spinning around. There's going to be centripetal acceleration here. That's A sub c. There's going to be tangential, let's make this one a velocity, tangential velocity. So what this is telling you is that this particle is moving in a counterclockwise direction, because at this point it's trying to go up, right? This is good old Newton's first law. We're trying to just keep doing what we're doing, but it gets brought back in because there is a force. There's a centrally pointing acceleration that brings it back in, and it's going to continue to move in this direction. A tangential acceleration is also going to be pointing tangent. I'm actually going to draw it this way just so that we can not have it be in the way of v sub t. Now, if this is the setup, what's happening right now is that this rotation is slowing down. This tangential acceleration is trying to work against the velocity. So it's trying to create that shrink that tangential velocity until eventually it becomes 0, and then it's going to start going the other way. So if this is our setup, it currently is rotating counterclockwise, but is going to slow down and then eventually start rotating clockwise. So that's where these things are on our picture. And we kind of got to last time where omega points. And I just want to remind you that omega either points outward, right? It's always perpendicular to the plane that holds our circle or our curve path football. And it's going to be pointing upward or outward if we're going counterclockwise. And it points inward or downward if we're going clockwise. So right now, omega would be coming out towards us, away from the board, because we're currently rotating counterclockwise. Okay, but just remember that omega doesn't really mean anything physically. That vector doesn't actually mean something physically, but we use that vector just to help us present which way it's going. And you can use the right-hand rule. Remember, you just curve in the direction of travel. Right now it's moving counterclockwise. So my thumb is pointing this direction. That's the direction omega points. Okay, so use the right hand. Right hand. So these were all the different things, but we also have some formulas that relate all of those. So let me go ahead and bring those back as well. So in terms of arc length, the big formula to remember is S equals R times theta. This case, theta must be in radians. But if our angle is in radians, then the arc length is actually equal to just the radius times the angle. From this, we get that omega is actually equal to R times V, where V is our linear velocity. Oh, sorry, got this backwards. This V is equal to R times omega. So our linear velocity is actually equal to R times omega. And then again, this would be our tangential velocity. And then our tangential acceleration, if we differentiate with respect to t yet again, is equal to r times alpha. So this is how you can find the tangential bits. And notice that all these equations have kind of the same form. If you want to know angular or radial acceleration, I apologize, the centripetal acceleration, this is one that I mentioned at the very end. And I said, oh, Kathy must have shown this to you. And you guys all went, no, we've never seen that before. So when you have an object that's moving in a circle on a circular path, this centripetal acceleration is actually equal to v squared over r. You can derive this using Newton's laws and how vectors play out. If you actually draw, we've got a tangential velocity, and then we find another one, and you look at what vector has formed to pull the one in, it turns out that its magnitude is equal to v squared over r. So if you'd like at some point, I can derive that. I'd rather not. So I'm just going to recommend you go back and look. I don't know which chapter it's in, but it's going to be in one of the earlier ones, like chapter 3 or 4 or something like that. But we're going to make use of this a lot. We need this because centripetal acceleration is kind of a big deal. And before we do some actual, like, real life calculations on things that are spinning, I want to talk about why we care about tangential and centripetal acceleration, why we break them down into the two pieces. So you remember what acceleration is, right? It's your change in velocity, right? So acceleration changes velocity, but velocity, being a vector, it can change in two different ways. I'm tired of looking at that screen, so I'll look at you guys. So velocity can change in two different ways. One, it can change direction. I can have the same magnitude but move in a different direction, and that's a change in my velocity. So acceleration can cause a change in direction of your velocity. A change in direction of velocity also means a change in direction of travel, because hopefully you remember that your position vectors follow the velocity vectors. They go in the same direction. Right? Okay, so one thing acceleration can do is actually change direction. The other thing it can do is change the magnitude of the vector, right? We can not change our direction, but increase or decrease our velocity vector's length, which means we've increased or decreased our speed. So acceleration does two things, or can do two things. It can change direction, or it can change speed. Well, that's what the two different accelerations, tangential and centripetal, do. If we're traveling on a circle, the tangential acceleration changes your speed. So if you've got tangential acceleration, your particle will be speeding up or slowing down. The centripetal acceleration is the one that changes the direction. So there's always going to be centripetal acceleration if we're traveling on a circle. Any curve for that matter. Like, think about this: when you drive and you're going over Echo or something like that, and you hit a curve, think about what you feel, right? You feel like you're being thrown to the side. You're not getting thrown, you're actually not getting thrown to the side. You're trying to keep going the same direction. And what's happening is the car is coming towards you. It's accelerating centripetally. And so because you're on a curve, there's centripetal acceleration. Okay, so that's why we break it down into the two. That's why we even care, because one changes velocity, the other one changes, one changes speed, the other one changes direction. All right, so let's actually put this into play. Let's take something that's rotating and do some calculations and see how this all plays about. All right, so here's the example we're going to do. Any questions before I do that?
I have a quick question.
Okay, go ahead, Bradley.
So I know circles can't necessarily be differentiated because they can't pass the vertical line test, but Is tangential acceleration and velocity first and second order derivatives?
They still are, yeah, but there are derivatives of the position vector. So what we'll do is we'll describe the location on a circle with the position vector, the x and y coordinates, and then that's what we differentiate to get velocity, and then differentiating that gets our acceleration. But that's total velocity and total acceleration. And you actually can differentiate a circle. You have to do it implicitly, if you remember your implicit differentiation. But here we're doing it vector derivatives, and we're using vector to describe our position. So, but yeah, velocity is still the derivative of position, and acceleration is the second derivative of position. And it's still the same if we're talking angular quantities. Angular velocity is the derivative of your position, your angle position, right? And then angular acceleration is the second derivative of a position function in terms of angles.
Okay.
All right, other questions before we dive into an example? All right, hearing none, let's look at this guy.
So let's say that we've got a rotating wheel, and what we know about it is that it's got an omega of 6 radians per second. So we'll make it a bike wheel. The spoke's coming out. And it's turning with omega equals 6 radians per second. And again, in general, it is going to be radians, because we want this stuff in radians so we can use those nice little formulas. All right, so here's what I want to do. I want to find what its tangential acceleration is when we're out on the edge. So I need to give you a size of this as well. But let's just say that this has got a radius of 1/2 of a meter. Okay. So it's a meter in diameter, but it's a radius of 1/2 a meter. All right, so let's just think about what we know about this. If we're out on the end, let's think about a point that's out here. Let's calculate some things. First, let's get its tangential velocity. How fast is that thing moving tangentially?
It would be 0.5 times 6, right?
There you go. Yep, it's just r times omega. So 0.5 meters times our 6 radians per second. And the nice thing about radians is they actually are dimensionless. That's why when we did things back in trig with radians, we didn't put a symbol or anything. We just, what's the angle? 2 pi, which is the number 2 pi. So multiplying these, we get that this is 3 meters per second. So an object that's out, if we've got something at the very tip of this, at the edge of this rim, it's going to be moving at 3 meters per second tangentially. Right. Now, there may be a component of velocity that's centripetal. It really kind of depends on how this thing is spinning. But if we've got a constant omega, then that velocity is all tangential. It's only if we have a variable omega that we'll get a velocity vector that doesn't point tangent. All right, so there's that. Since I just said that we've got a constant omega, we actually know that alpha is 0. And this is going to be radians per second squared. But this is only due to the fact that I just said that omega is constant. If we had a variable angular velocity, then alpha would be different than 0. All right, well, if alpha is equal to 0, that means that the tangential acceleration is also 0. Because remember, it was AT is equal to R times alpha. So times 0 is going to give us 0. So remember I told you that tangential acceleration is what changes the speed, which tells us that this particle is always going to be traveling at 3 meters per second, no matter where it is on the circle. And this we kind of get when we have rotation that's going, especially horizontally, if we don't have to worry about gravity. So if we're just going horizontal, that's where we can approximate constant omega a little bit better. But we also design things so that they do this. Now, I know most of you are way too young for what I'm going to talk about, but they're making a comeback. Think about record players, like a turntable. When you play a record, you set a speed. There's 33 1/3 RPM, 45 RPM. There was also 78 back in the day. But that's revolutions per minute, which is an angular velocity. And so those things were designed so that they went around with the same constant angular velocity. That way you had a constant speed, which meant you could make the information in the grooves. Like, I don't know if you know how records worked, but you basically had a little needle that would kind of bounce up and down as it hit grooves, and those little bounces translated to sound. And because it had constant angular velocity, that allowed people to make records so that the spacing of all those little bumps was always the same to produce the sound. So if you've got a rec player, then that's how that works out. Anyway, so there's our tangential acceleration. So let's find our radial acceleration, our centripetal acceleration. So the centripetal acceleration is equal to v² over r. And that v is a tangential velocity. So we can go ahead and just plug in those numbers now. We already calculated it. It's equal to 3² divided by 0.5, which is 18. And this is going to be 18 meters per second squared. Because remember what your units are, the v is meters per second. So squared is meters squared per second squared. And then the radius, that's another meter. Now, alternatively, we could have figured out this centripetal acceleration without calculating the v. We could have done it a little bit faster if we had substituted this r omega in for the v. So check this out. We've got our AC, it's v² over r. We know v is r omega. So I can just throw that in there. So if I square that, I'm going to get r² omega² over r. One of those r cancels. And so we get r times omega². And I want you to notice that we get exactly the same thing here. Omega is 6, so squared is 36 times a half. Well, there's your 18 meters per second squared. So it's kind of nice that you can get to centripetal acceleration knowing just the angular quantities, because sometimes we don't want to have to go through all that work to find the linear quantity. All right, so there is an example of how we can use this sort of stuff to figure out what's going on with a rotating object.
If we picked another point, like if, say the radius was still 0.5 meters, but we picked another point, we would have to change the radius, right?
Correct. Like if we were going to look at a point on one of the spokes, say right here, then we would still use the same formulas, but we would change r, because this r is the radius of the circle of travel of our point. And if we're at a point in here, it's going to do a circle, right? It's still rotating about this point, but it's not all the way out. So we would have to actually calculate that r. So let's say that that was 0.2 meters or something like that. then we could go to all these computations, but everywhere there's an R, we would put 0.2. And what you're going to see is it doesn't travel as fast. Its velocity is going to be less. Linear velocity is going to be less. We're also going to see a change in the acceleration, right? The angular or the centripetal acceleration is also going to be less because of the smaller R. But yeah, it's all dependent upon the point itself where you have it.
Okay.
Is that why it's better to sit in the middle of a merry-go-round if you're, get dizzy easily as opposed to the outside of it?
Yeah, let me
Look at you guys a little bit. But yeah, so think about merry-go-round. If you are near the center, it's a lot easier on you in terms of dizziness and all that because you're going slower. You're actually not going as fast linearly. You're also experiencing a smaller centripetal acceleration, which means it's easier to hold on. You may remember that when you were a kid and you're on a merry-go-round, if you're out on the very edge, it's crazy hard to hold on because there's so much more centripetal acceleration. And it's that centripetal acceleration that you have to counter in order to stay on, right? You have to supply an equivalent acceleration to not be thrown off. They don't really have merry-go-rounds much anymore because, everybody gets hurt when they're on them. But if you ever get the chance and kind of access to one and can play around, I know there used to be one over down at the park in Myers. I haven't been down there in a while, but you'll notice that it is much more difficult to hold on the outside because you have a much greater AC. All right, other questions? All right, let's pause for a little bit. On my clock, it's 4:12. I'm going to come back at about let's say 4:18. So we'll take 6 minutes here. I'm going to pause the recording. And then, all right. So the next thing we're going to talk about is how the relationship between all these angular quantities. And we can build kinematic equations for these just like you did for linear quantities. So you probably remember back in the very beginning of physics where you went to let's say we've got constant acceleration. What does that tell us? And you derived all these formulas that involve velocities and times and the acceleration. And it turns out that every single one of those equations has a related angular quantity equation because they were all built the same way. And so these get built the same way also. So I want to remind you about them. At least I'm going to show you what they look like in angular quantities. And this will probably bring back some of the memories from first quarter physics when you had all these linear quantities. So I'm going to switch to the board.
So let me start with this. We're going to assume that alpha is constant. So if we've got constant alpha and we want to calculate omega, all we'd have to do is integrate. So we'd have that our omega is going to equal the integral of alpha d theta. And this is important. It's actually going to be a d theta because we're looking at angular quantities, right? Oh, it's still a dt. All right, so if we integrate this thing, we're going to get alpha t plus some c. That c is actually going to be our initial angular value. If we let t equal 0, then c is going to be the omega at that time. And so how we would translate this into a formula that you're used to seeing would be something that looked like this. So do you remember seeing something like this with V, where there was the V final is equal to AT plus V initial? Thumbs up, yes. Thumbs down, no, you don't remember?
Yes.
I'm getting some thumbs up. So this was one of the very first things you guys did in first quarter physics. So this is exactly the same. If you want to know a position, you would integrate this, right? So our theta would be an integral of the alpha t plus omega naught. So this is going to give us 1/2 alpha t squared plus omega naught times t plus c. This c, that's going to be the initial position, but initial angular position. So we would get another formula here that would look like your final angle is 1/2 alpha t squared plus omega naught t plus theta initial. And so if you go back and you look at what you did in the first quarter with linear quantities, same deal, except these were your x's, your x final, x initial. So we've already built 2 of those kinematic equations just by doing the calculus, right? We just integrated. But the other ones you can get by eliminating one of the variables. So like if we solve this first one for omega naught, let's say, or alpha, let's say we solve this for alpha. You could take that, plug this into the second equation, and it's going to give you another one of the kinematic equations. I'm just going to start writing them up here. And that one would be the good old theta final minus theta initial, the difference in the angles, is equal to 1/2 omega naught plus omega final times t. So you may remember there was another one that looked like that for linear quantities. The change in x is equal to 1/2 the sum of the velocities times t. So there was another one that we got by eliminating alpha. Well, you could also eliminate t. So if we solved this for t and plugged it into the second one, what we end up getting as a final one would be that the omega final squared is equal to omega naught squared plus 2 alpha times theta final minus theta initial. Sometimes you'll see that one with like a delta theta. You probably had a delta x for the ones that were linear. So those things that I've got boxed, these 4 equations, are identical to the linear quantities, or the linear equations, just with angular quantities instead of the linear quantities. So the good news is that when we deal with things that are rotating, we don't do anything differently than we did with those that were linear, right? We're just going to put in what we know and figure out what we're missing, and determine, using that, using the right formula, we'll determine what we need. So here's an example. So I'm going to leave this here for just a sec. So let's say we've got a wheel spin. So another bike wheel like we had before. And let's say that what we know is that initially we've got an angular velocity of 4 radians per second. So that means in every second, we're going to do 4 radians, which is just slightly under 2/3 of a rotation, because a rotation would be 2 pi or 6.28. All right, so quiz for class. Thumbs up if it's clockwise, thumbs down if it's counterclockwise. Which way is this rotating? Clockwise, clockwise or counterclockwise?
Counterclockwise.
So I heard a counterclockwise. I've got Jesus gave me a thumbs up. Ralph is clapping, I think is what that is.
Yeah, it's the best. We don't have a
So
thumbs down.
Bradley and
Clap and a thumbs.
okay, so we're getting a couple more counter. Oh, there isn't a thumbs down.
Yeah, there isn't. So clap
I
is
did not.
thumbs down.
Okay, so from here on out, it'll be thumbs up and then clap is thumbs down. Okay, so then I guess the clap, thumbs down, counterclockwise.
Clap.
So this one is rotating counterclockwise. Positive omega means we're rotating counterclockwise. So right now, this thing is spinning this way. All right, let's apply an acceleration on it. We're going to have an angular acceleration of negative 1.2 radians per second squared. So what does this mean? What's happening to the rotation?
It's accelerating.
All right, it's definitely accelerating because we have non-zero acceleration. But what does that mean in terms of the spinning of this? Is it going to be spinning faster? Is it slowing down? Is it changing direction?
Changing direction.
So Victor threw out a getting slower. Cesar went faster. We heard Bradley say changing direction. So I guess everybody thinks one of the things I said was right. All right, so negative acceleration means that this omega needs to be going down. So if omega is going down, that means we're slowing the rotation. Eventually, that omega is going to turn negative in a little more than 3 seconds, right? Just around 3.5 seconds. This thing is going to now have negative omega, which means it's going to be spinning clockwise. So what's happening to this is this is spinning, it's slowing down, stopping, and then starting to rotate the other way, and it's going to continue speeding up rotation in that direction. So that's how to interpret this. All right, so let's do this. Let's calculate what's the omega after 3 seconds. So I'm going to put here at t equals 3, what does omega equal? So basically all we have to do is look at which of these equations has an omega final, because that's really what we're looking at, but also has t, omega naught, and alpha. So in terms of which one that is, that's going to be the third one. So if we want to calculate this, we just have to plug in our values. We're going to get our alpha is minus 1.2. We need to multiply that by time. Well, we're going 3 seconds. And then we'll add to it omega naught. So that's our 4 radians per second. So we get minus 3.6 plus 4. And so that omega is actually 0.4 radians per second. So it's still rotating in the counterclockwise direction. It's just going much slower. All right, so how about this? What if we started with a point, we mark one of the points, and we're going to look at the point that's directly out in the positive x-axis. Okay, so that point right there. Where is that point going to be in 3 seconds? How are we going to figure that one out? Because this point, I mean, obviously it's going to be somewhere on the edge of the wheel, but I want to know, where's it going to be? Is it going to be back here, down below? All right, so Victor just threw on the chat theta final. And that's exactly how we're going to do it. We're going to see if we can find theta final, because then that will tell us where this point needs to be. All right, so obviously we need to use one of the ones with a theta final, which means not the one we just used. So we have a whole bunch of options. The one I would pick, well, how about I'll ask you guys. You want number 1, 2, or 4? Just throw it in the chat. 1, 2, or 4.
I think 4.
All right, so Bradley threw out a 4. Max says 4. Ralph says 4. 4. Victor says 1. Jacob said 4. All right, well, if we go with majority rules, I guess we're going to have to go with number 4. Turns out it doesn't matter. Any of them will work. But let's go to number 4. So let's think about what we know. We want theta final. We need to know alpha, which we've got. We need time. We got that. Omega naught. We got that. Also have time. And then theta initial. Let's go with standard position so that that's 0 radians. So if we use number 4, we can go ahead and get all that and put it in. Let's see what we get. We get theta final is going to be 1/2 minus 1.2 times 3 squared. And please apologize my lack of units. I'm just tired and don't want to use units anymore. So we're going to have omega naught is 4, the time is 3, and then theta, well, we said that was equal to 0. All right, so we can punch that in, and if my numbers are correct, what I calculated earlier, I get 6.6. But what are the units on this? 6.6 watts.
Radians.
Yeah, this is radian. All right, so where is that going to be? This one might be a little bit hard to describe in the chat box. Do you have a good concept? So Victor just said more than 3 circles. It actually hasn't done 3 rotations, believe it or not.
It's done 1 rotation. It's in first quadrant.
Okay, so it is going to be in the first quadrant. It's done just a little more than 1 rotation, because 1 rotation is 2 pi. 2 pi is 6.28. So this is a little bit more than that. It's an extra 0.3 radians. 1 radian, just ballpark, is around 57 degrees. So 0.3 of that is going to be on the order of, what, 18 degrees or something like that. So it's actually going to be located just barely past where it was. So be careful with these. When you go to radians, think about the decimal equivalents of pies. That will help you. So if you have a number that's around 3, well, it hasn't quite gone pi, so it's in the second quadrant and so on. But that's where that particle would be at this point. So can you think of a real situation where we would care about this? Probably not a bicycle wheel, right? You're not really caring about this point on the end of a bicycle wheel. But can you think of a real life situation where we care about angular position?
Planetary rotation.
Oh yeah, that's a huge one. When we have planets in nearly circular orbits, like Earth's is fairly circular, it's a good descriptor of where we are. Other places where this matters are things like particle accelerators. Like when you go to CERN,
or down to Berkeley, or these other places that have particle accelerators, a lot of them are circular because it's really easy to get go long distances if you're in a circle. You just keep going in circles, and so you can get stuff sped up, as opposed to, imagine if it was actually linear, you're going to run out of space, right? So a lot of those are circular, and they need to know where things are and what's going on. And so anytime you have stuff traveling in circles, it's something that matters. Will it matter to you in your future career? I don't know. I don't know what you're going to end up doing, but it's definitely something that we should be aware of. All right, so we've got these quantities that are very similar to linear quantities. They actually follow the exact same formulas, which is awesome. And so we've got angle equivalent of position. Omega is the equivalent of V. Alpha is the equivalent of A, which should probably make you start wondering, what about all the other stuff we've done with those quantities, right? Like energy. We know we've got kinetic energy. Is there an angular kinetic energy? Or momentum. We've got linear momentum. Is there angular momentum? And it turns out that yes, for all of these things, there's an equivalent angular form. So what we're going to do next is we're going to talk about energy. We're going to look at rotational kinetic energy and what that means, and what we need to know in order to calculate it. Okay. So let me go back to the board.
And let's talk about the kinetic energy of something that's spinning around in a circle. So we're going to start easy and just go with a point mass. We're not going to worry about extended objects just yet, but let's just say we've got a point mass that's going around in a circle. So here's our circle. Here's our point mass. And we'll give it a mass of m, call it good. We'll also say that the circle is a radius of r. And what I'd really like to do is figure out what kind of kinetic energy it's got. So we know kinetic energy. It's just good old 1/2 mv squared. So what we really need to know is how fast is this thing traveling? Well, you may remember that there was a way to relate velocity to these angular quantities. We had v was equal to r omega. Let's put that in here. So we're going to get 1/2 m times r omega squared, which I can distribute the square and kind of manipulate a little bit. I'm going to rewrite it as 1/2 mr squared times omega squared. And I'm even going to put some parentheses here around the mr squared for a second. So notice that this formula now is based only on angular quantities. The amount of kinetic energy obviously depends on the mass of the object, but then it also depends on where it is, how far is it from the axis of rotation, and how fast is this thing spinning. So if you look at that, it looks pretty similar to what we had with the linear kinetic energy, right? Linear kinetic energy, we have 1/2 something times v squared. Well, since this has the same form, we're going to replace that mr squared with another letter, and we're going to use capital I. And now these two look pretty much the same. We just have an angular quantity and this new weird I thing, where I is equal to mr squared. And this is our rotational kinetic energy. It's got exactly the same form, we just have different quantities. So this guy I, you probably have seen this before. In fact, I know you've seen it before, but not in physics. You saw it in calculus. This is the moment of inertia. And since I wasn't there, and I don't know what Larry told you, did you guys really talk about what the moment of inertia was? Or did you just learn how to calculate it?
Mostly just how to calculate it.
Okay, that's what I figured.
You did get a very basic overview about what it was, but yeah.
Okay, so here's how you want to think about I.
The moment of inertia is basically the equivalent of mass. Like you look at that formula, it takes the place of mass in the kinetic energy formula. So think about what mass is. And this is something that we don't usually think about, right? Like, suppose I ask you to define mass. What is it? And
MGH.
you might go, well, it's the amount of material an object has, right? But then you go, well, but is that really what that means? Because not all materials have the same mass and all that. And so mass is kind of one of these.
It's like, isn't it like what Victor said, like the quantity of inertia in an object? Or...
Okay, so what does that mean? What's the quantity of inertia?
Its capacity to resist changes in motion.
Okay, and that's where I like that, Jacob. That's kind of where I go with mass. When I tell people, if they ask me what mass is, I say it's the ability of an object to, resist changes in motion, right? You go to Newton's second law, good old F equals ma, right? The greater m is, the lower a is for a given force, right? So when you apply a force to a really massive object, it doesn't accelerate much, right? This is why you can't go and just push a steam locomotive.
Yeah.
Right? I mean, good luck. But you can go out and you can push a tennis ball, no problem, because it's got a way smaller mass. So mass is really the ability of an object to resist accelerating. So moment of inertia is the exact same idea, except it's not now the ability to resist linear acceleration, it's angular acceleration. And angular acceleration is changing your rotation. So think moment of inertia is really the property of an object that basically fights changing its rotation. If you have a really large eye, it's going to be very difficult to change how that object is rotating. If it's got a very small eye, it's super easy to change its rotation. So for example, I just have a little thing. I just have on the end of a pen, I've got a wiffle ball. And you can see there's a green dot, just FYI, there's a little green dot if we want to keep track of where we are. But this thing, I can actually cause it to rotate really easily. Right now it's got 0 rotation, right? Its angular velocity is 0. It's not spinning. I can apply a force. I can actually cause it to rotate, and it's not that hard, right? I can use one finger to make it change its angular velocity. So it's got a pretty small moment of inertia. Now imagine I had a bowling ball and the same kind of deal where a bowling ball, I drill a hole through it and I put it on this pen. Well, first of all, this pen's going to break, but if I give it axis rotation, it's going to be hard for me to spin that bowling ball. I'm going to have to apply a significant amount of force to do that. So it's got a large I. It's got a large moment of inertia. So that's what you need to think of I as, is it's the ability of an object to resist changes in spin. So let's look at this again real quick, because I gave it some angular velocity, right? It starts at 0, I speed it up. Whoops, lost my axis. Let's try that again. Spinning too hard. But eventually it stops. So something's slowing it down, right? So what is that something?
Friction.
Yeah, it's friction. There's friction that's supplying a force that's going to then create a slowing down of this thing. So friction itself is creating an alpha. I created an alpha by doing that. Friction created an alpha to slow it down. They're both happening at the same time. And we'll talk about that as well. All right, so Ian, you just asked, can the shape change? And okay,
yeah, so if it's the same massed object, let's say a wiffle ball, but it's a triangle.
Oh, okay.
It'll have the same ability to spin.
Ah, gotcha. All right. So if you have the same mass object, so we're going to take this and take all of the plastic and change it into a different shape, like a pyramid or a box or something like that. So the question is, does that change the moment of inertia? Yes, absolutely. And we'll actually talk about that. We might get to that today. If not, we'll definitely talk about that on Monday, how you how shape definitely matters when it comes to moment of inertia. So not only
object or something could
say that again.
Something even like a lopsided object.
Yeah, lopsided objects, if we were to take this mass and distribute it in a different way, it would absolutely get a different moment of inertia. So things that are lopsided tend to have really weird spins.
Yeah.
Because of that, because of the mass distribution. And we'll see how that matters today, how mass distribution affects your moment of inertia. All right, so that's what I is. It's really just the resistance to changes in rotation. And so then the follow-up question, Ian, you just said, would that be due to friction too? Was that the slowing down?
Yeah, like also like certain levels of friction might, like because of surface area, might change.
Yeah,
like
and
more wind resistance.
And shape definitely matters there, especially with air resistance. Since we live in a place where we're in a fluid, that definitely matters. Now, something like if we're on the moon, you know, that aspect of it, the shape aspect won't have anything to do with air resistance and friction, other than potentially the friction on the axis itself, like the pen or whatever else we're spinning on. But the shape still will change its moment of inertia, the eye.
Okay.
But here's the other thing that's kind of crazy about the moment of inertia is that it depends on the axis about which we're spinning. You know, when I had this set up, so I've got it spinning around a central axis, that's going to be different in terms of my ability to spin it or the energy I need to put into it or whatever to cause it to spin than if the axis is, say, over here. Now, this one I can't physically do because the ball would kind of be spinning around the axis this way. And unfortunately, gravity won't let me do that. But this is going to have a different moment of inertia. Even though it's the same object, it's spinning in a different way. And you can definitely experience this. And I will give you some real life ways that you can experience this to see how changing the axis will change how easy or hard it is to spin something. Okay. But I'll save that for another day. So let's talk about how we actually calculate this moment of inertia when we've got like an extended object. So I'm going to go back to the whiteboard. This is going to be a kind of a little review of some stuff you did in calculus last quarter, or in Ian's case last year.
So what we know about the moment of inertia is that it's mr squared, right? I is equal to mr squared. So when you have just a single object, a single little piece, it's really easy to do this because all you need to know is its mass and how far away it is from the axis of rotation, and then put them in. Now, if you have a collection of points, so let's do this. Instead of just having one point, let's say we've got like 3 points that are somewhat connected to each other or something like that. And we want to find the moment of inertia of this. What we would have to do is figure out for each one of them how far away they are from the axis of rotation and multiply their masses by the square of those distances. So what we would get, like for the first one, would be m1 r1 squared. Then we would add to that m2 r2 squared, and then add to that m3 r3 squared. So it's kind of nice. You can take the individual moments of inertia and put them together and just add them up. And this is what we use to turn this into an extended object that is just continuously distributed. Notice that we could write this as a sum. This is really just the sum of the mi ri squared, and the I is just however many pieces we have. So if we go to an extended object, something that looks like, you know, the good old classic blob, thing, and we want to find out the moment of inertia, what we're going to do is just break it into a whole bunch of little chunks. And you guys have seen enough calculus by now that you know what's going to happen. We're going to do this with a whole bunch of chunks. So we're going to have this sum that then goes to infinite. And if it goes to infinite, that of course means we now have an integral. So the way that we're going to define it is that the moment of inertia I, it's the integral of the mr squared. And you notice I didn't put a little differential in there because sometimes we want the differential to be a differential mass. Sometimes we want it to be a differential r, but usually it's differential mass. And so what you did back in the day in calculus, and what I'll show you again with an example today, is that this is going to be an integral of r squared dm. So we look for all the pieces that are the same distance away from our axis of rotation. We figure out what the mass of that thing is, and we do this integral. So you may remember this. I hope you remember this somewhat from calculus. But let's see if we can do this. Let's see if we can actually calculate the moment of inertia of an object. And we're going to start with kind of an easier one. Let's look at a cylinder. And this is going to be a solid cylinder. So it's not a shell. It's actually just nice and solid here. So imagine that we went and drilled out from a piece of wood just a peg. So it's like a wood peg. And we're going to go ahead and rotate it about the axis that goes right down smack through the middle. So this thing is just spinning around like that. Here's an example real quick. So imagine that this is solid. Obviously it's not, right? But imagine that this was solid. It's rotate. We're spinning it. I don't know if you can see that with me, but we're spinning it that way, right? So we're rotating it about its central axis. All right, so that's what we're doing. We're going to see if we can calculate this guy. So here's the trick. What we want to do is think about all of the pieces that are the same distance away from this axis of rotation. So if I were to specify an r, so let's just say I come out here a little bit r, what are all the points that are a distance little r away from that going to look like?
The top and the bottom.
The whole shape. Like on the top, what's it look like, Bradley?
The circle.
Okay, so you're going to see the circle up here. You're going to see a circle on the bottom. And everywhere we slice, we're going to see a similar circle. So what we're going to get is a cylindrical shell. So you remember when you guys did all that volume stuff, and one of them was volumes by shells? That's the same idea. This shell, this is the thing that holds all of the points that are a distance r away from that central axis. So what we need to do is figure out what is the mass of that little cylindrical shell. So to figure out the mass, you need to know the density, and then you multiply density times volume. So we're going to build our dm. dm, we need density times volume. And let's assume constant density. If it's not constant density, this is a much more difficult thing to calculate, but you would just put the formula for density and put it in and do your thing. But we're just going to leave it as rho. Now, if we want to find the volume of that shell, the volume of that shell is going to be the same as its area times its thickness. So I'm going to put here area times thickness. And again, use my little Nevada drink koozie here to show, here's your cylindrical shell. If I want to know the volume of this, if I can imagine I just cut down the edge, and I kind of unravel it, it's going to be whatever that area is times the thickness. Okay, well, the area of that, it's going to be a rectangle. Let me show you with a piece of paper. So I've got a piece of paper. If I just roll it up, here's your cylindrical shell. I cut it and I unroll it. It's a rectangle. So the question then is, well, what's the area of that rectangle? Well, the area of that rectangle is going to be the circumference of that circle, that's this side, times its length, its height. So if we put this all together, we're going to get rho times 2 pi r, that's the circumference of this guy, times L. Let's go with this thing is length L. So there's its area, and then its thickness, since it's a little tiny shell, its thickness is going to be a differential, and it's going to be a differential r, a little tiny deal. So there's our dm. It's going to be rho times 2 pi rl, that's the area, times dr, which is our thickness. So let's put that up in here. And so when we calculate our moment of inertia, we're going to get I is equal to the integral of r squared times this. So I'm going to kind of put stuff together. I'm going to get 2 pi rho L r cubed dr. So it's an r cubed now because there was one r in our area formula, and there were the 2 that come from just the calculation for moment of inertia. Whew. Well, we're still not done because we need bounds. So we need to think about what are the bounds on the radius on this little r. Well, little r can be 0. That would be we're right on the axis. But the biggest is going to be whatever the radius of the cylinder itself was. I'm going to call that capital R. Go ahead and put this guy there as big R. And now we're ready to integrate and do our thing. So I'll leave this to you to integrate. I mean, you can trust me or not. You can check it yourself. But you're going to end up with 1/2 pi times L times rho times big R to the 4th. So notice what this depends on. It depends upon the length of the cylinder. And that should make total sense. Because if it's a longer cylinder, it's going to be harder to rotate. There's more mass, it's going to require more energy, so it's going to be harder to spin. Think about like a quarter. So think about like a quarter and spinning a quarter, or spinning a big old cylinder of quarters, like a roll of quarters. Which one's easier to rotate? Well, obviously the single one is. So it depends on L. It depends on the density. That should also make total sense. If it's a heavier, more, a more dense object, it's going to be tougher to spin. And it also depends on the radius of the thing. So a small disk is going to be easier to rotate than a large disk. So it kind of makes sense that all those things should matter. But for this shape, this is what it's going to look like. If you look in the physics book, they've got a table of moments of inertia, but it doesn't look like this. It doesn't look like this formula, because what we like to do is actually get it in terms of the mass of the object. So here's what we're going to do. Let's look at the same object, but let's figure out what its mass is, and then replace that into this formula. So if we go to the whole thing itself, its mass is going to be density times volume the volume, since it's a cylinder, that's going to be pi r squared times L. So that's what the mass of this entire thing is. And if you look down here at this moment of inertia, you see that there's a rho, a pi, an r squared. We have r to the fourth, but there's an r squared in there, and an L. So I'm going to replace those two r's, this rho, this L, this pi, with an m. And so what we find out for this cylinder is that its moment of inertia is equal to 1/2 mr squared. So we just calculated the moment of inertia for a cylinder being spun about the axis that goes down through the center. If we change our axis of rotation, we change this I, but this is what it is. And this is what's interesting, is it doesn't actually matter what L is. You notice that L's no longer in there because the L gets incorporated into the mass. So if you have something that's thicker, like you know how I said, let's go to a roll of quarters as opposed to a single quarter, well, that L got incorporated into the mass, and you can see how, yes, it's going to be a little bit tougher to spin. All right, now you can do this with any shape. You can do it with a sphere. You can do it with a rod. You can do it with a plate. When you were in calculus, you did this for lots of different shapes. This isn't calculus class. I'm not going to make you derive a lot of these because we want to use them. Instead, we want to use them. So you probably want to make note of what page has all those moments of inertia, or find a really good resource for that so that you can look at a shape and figure out what its moment of inertia is from the chart. Anyway, so there's your moment of inertia for a cylinder through the axis. So is this kind of bringing back some of the memories from last quarter? Kind of remember doing stuff like this?
Yeah.
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 Okay. So I'm not going to really do more of them, but I just want you to notice that this is how you go about doing it. I definitely like the cylinder just because if you look at this formula, 1/2 mr squared, like everything is that kind of form. Kinetic energy, 1/2 mv squared. Angular kinetic energy is 1/2 I omega squared. Here's another one that's a 1/2 mr squared. All right, but there is a theorem I want to show you, and I think this is where I'm going to end today, is what's called the parallel axis theorem, that lets you take something like this, where we already know the moment of inertia about one axis, but change the axis so that instead, let's say we are going to be rotating about an axis that's adjacent to the side, we can use the parallel axis theorem to get this moment of inertia quickly instead of having to go through the whole calculus thing all over again. And that should make you happy, right? Because these are a pain. These are definitely a pain to get set up and are kind of tricky. So let me show you the parallel axis theorem. I will prove it for you because it's pretty easy proof. But it basically goes like this. If you want to know the moment of inertia through some parallel axis, I'm going to call it P, it's going to equal the moment of inertia of the axis that goes through the center of mass plus m times d squared. The m, of course, is the mass of the object. That's probably pretty obvious. The question is, what is d? And d is just the distance from the axis to the center of mass. So all we need to know is how far away it is from the center of mass in order to do this calculation. So I want to actually show you how we apply this before we prove it. And we'll do exactly what I was saying. Let's take the cylinder that we just did, but instead rotate it about an axis that's over on the edge. So now we're spinning like this, right? So that's a different kind of spin than what we were doing before, right? This versus a rolling kind of spin. So we should expect a different moment of inertia, and we will see that here. All right, so let's first think about what we know about the center of mass. We know that its moment of inertia was 1/2 mr squared. Okay, but now we need to add to that md squared. And so we need to know how far away from that center of mass axis is our new one. So really, we just need to know what is that distance right here. And hopefully you can see that's pretty easy. That's just our radius. So this is going to be 1/2 mr squared plus mr squared, which is 3/2 mr squared. So a couple things. First, notice how fast that was. That was crazy quick because we didn't have to go and rederive everything. We just need to know that this theorem actually works, and it does. We'll prove it. So it was way, 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 way quicker. So that's why you'll see charts of all of these things that have center moments of inertia about center of mass, because we can then use those with parallel axes. The other thing, I just want you to think about what this means. So this is now 3/2 mr squared, which was more than what we saw when we were going around the regular center of mass. So what that means is that it's harder to spin a cylinder like this. It's harder to take a cylinder and spin it around an axis on its edge than one in the middle.
See, that's interesting that you say that, because it just made me think of the Earth rotating, and it makes sense that it'd be easier to rotate on a center of mass axis than some dumb on the side axis.
Mm-hmm. Yeah, if you think about in your experience with things spinning, you kind of know this. And this also gets back to what Ian was talking about. Remember, actually, hold on a second.
I want to come back to this guy. Remember when Ian was talking about if your mass gets distributed kind of lopsided or weird? We know from our experience that that makes things a little bit harder to rotate. And this is exactly why. Think about that mass. That mass is now distributed in such a way that its R it's not balanced, right? And so it makes it a lot tougher to rotate. You can change your axis of rotation to improve that and make it so that that lopsidedness doesn't affect it as much. But we're used to this. You experience it. You really do. If you think about it, if you go out and you recognize what's going on. So my challenge to you actually with all of physics, whenever we talk about something, I want you to think about real life situations where you've experienced it. And going forward, when you get into an experience where you're doing something with rotation, pay attention to it and notice it, and you'll see a lot of the stuff that we talk about. You'll feel it, especially when we get to things like angular momentum and conservation of that. If you've ever applied your brakes too hard and gone over the front of your bike, you were experiencing conservation of angular momentum in a bad way. But we'll talk about that when we get there. So, but almost everything that you've ever experienced, we can describe, and moment of inertia is necessary when we talk about rotating things, because it plays the role of M. And you saw how important mass was with linear stuff. We definitely need it. All right, so let's prove this thing. All right, let's actually prove this parallel axis theorem so that we can use it and not be stuck doing calculus all the time. Not that calculus is bad. It's just, why spend the time if we don't have to?
All right, so here's how we're going to prove this. Let's just look at a slice of the object that we're rotating. So here's the slice, and this point right here, this dot right there, this is the center of mass. Okay. And what I'm going to do is I'm going to put axes that go through our center of mass. So our moment of inertia about the center of mass would be if the axis right here and we're spinning. But we're going to spin it around a different point. Instead, let's spin it about that point right there. And just for the sake of having some numbers and names and things like that, let's just say that this distance is A and this distance is B. So what we know is that the distance D that's going to matter when it comes to doing the parallel axis theorem, we know that D squared is equal to A squared plus B squared from the Pythagorean theorem. So let's just remember that. Now, let's look at the moment of inertia of a point somewhere out here. I'm going to put it, let's put it right here. So it's not on the edge, but it could be on the edge. It doesn't really matter. It's just some point that's on our object. Now, what I want to do is I want to look at the distances from that point to the dot and that point to the X. So I've already got that this is A and B. Let's use good old X and Y coordinates for this one so that we know this distance is X and this distance is Y. So let's first look at the moment of inertia about the center of mass. So about the center of mass, if we wanted to calculate the I for that thing, it's going to be m times x squared plus y squared. So when I write I center of mass, I'm talking about the moment of inertia of that one piece. What we'd actually have to do is add all these guys up, right? So let's just do that. It's going to be m times the x squared plus y squared for each one of those chunks. All right, so there's our center of mass. So now, let's look about the other axis. So for that one, we call it IP. It's going to be the sum, again, the mass chunk times the distance to this guy. Well, for that one, we have to use the distance formula. And so what we're going to get is x minus a squared plus y minus b squared. And I apologize, I kind of ran out of space there. But that's just good old distance formula.
Why are they squared? I don't remember the distance formula being squared.
It's Pythagorean theorem. Remember, we have our a squared plus b squared equals c squared. And
Okay.
so in my formula, since I'm squaring the r, I'm just going to leave it as the r squared.
Okay.
All right, so it's Pythagorean theorem. All right, well, let's take this one, the parallel axis, and let's just do some algebra on it. So we're going to get IP is equal to m times, we're going to have x squared minus 2xa plus a squared plus y squared minus 2yb plus b squared. So FOIL, right? We just need to make sure we FOIL all that out. And now what I'm going to do is I'm going to group them. I'm going to group them here a bit so that we get m times x squared plus y squared And then we're going to have plus m times a squared plus b squared. So that's all the 4 squared terms. And then we have minus 2xa minus 2yb. And there's an m times both of those. All right. So now let's kind of break those sums up and look at each one of them individually. So we have IP is equal to the sum of m times x squared plus y squared plus the sum of m a squared plus b squared. Those are those first two pieces. Then we have minus the sum of 2xam minus the sum of 2ybm. So those are those 4 different pieces. So the first one, recognize that as the center of mass moment of inertia. Okay, those are identical. So this becomes I center of mass. All right, the a squared plus b squared, we already saw that that was equal to d squared. That's how far away that new axis is from the center of mass. So this is going to be d times the sum of the masses of all the little chunks. Well, if we add up the masses of all the little chunks, it's the mass of the entire thing. So that becomes plus md squared. Okay, so then what about these other guys? Well, here's what we really want to look at. Look at the x times m, and in this case, the y times m. You may remember those as the first moments. And so basically what we're doing is we're taking all of those first moments and adding them up. And we're doing that in the x direction and the y direction. And if you do that, that's how you get the coordinates of the center of mass. Well, what were the coordinates of the center of mass? The way I had it drawn.
The origin.
The origin. So that makes both of those 0. So we get minus 0, minus 0, which brings us to the parallel axis there. So it's kind of nice. If you know the moment of inertia about the center of mass, then you can go about any axis and you're good to go.
So the moment of inertia for center of mass is equivalent to the 3 halves.
So the one that we calculated that we got the 3 halves mr squared, that was specifically the moment of inertia for the cylinder rotating at about an axis that was on the edge of the cylinder.
Makes sense.
Right? Where the one about the center of mass was only 1/2 mr squared. And that's the one that we actually calculated using the calculus.
Okay. So depending on the object, this is the more formal definition.
No, I wouldn't say that depending on that this is formal or not formal. This is just a tool that we can use to calculate the moment of inertia if we're not going through the center of mass. It's related to the moment of inertia through the center of mass, but we have to add on the md squared. It makes it super fast, Bradley, is really the whole point, is that if you know, like, okay, let's take this pen. And pens, like a rod is going to have a different moment of inertia than a cylinder. The moment of inertia of a rod would be 1/12 the mass times the length squared, because we're going with something that doesn't actually have another dimension. But anyway, so this one, if we know the moment of inertia spinning it, say, around the center of mass this way, we could then jump out to, well, what if I'm going to spin it about the edge? And all you have to do is take that original moment through the center and add md squared, where d is the distance away. So it really expedites calculations. That's the reason we like this parallel axis theorem.
Okay.
All right, so I think we're going to stop here for the day. Now that we've kind of got an idea of what moment of inertia means. And what we'll do next time is actually use it. We'll use it to calculate kinetic energies, and then we'll see how it applies to momentum and everything that M did, I is going to do as well, just in an angular way. So we'll have angular kinetic energy, we'll have angular momentum, which of course means we're going to have conservation of these things. And now we're going to be able to start seeing how things rotate. And we're going to have to describe how forces actually cause rotation, because it's different than how forces cause linear changes. So this is kind of where we're going, is we're going to continue with the building rotation the way that it goes, and then linking linear quantities, specifically force, to the rotation. And we're going to introduce this new thing called torque. Anyway. All right, so with that, let me go ahead and pause the recording.